Hello there, welcome to our ECE 3400 project for analog to digital converter or ADC design for an application of an ultrasound sensor that is used in a pulse echo sensing. For our project, we're giving these three specific specifications, which are input signal range, the resolution, and sample rate. The input signal range was from 300 millivolts to 3 volts. The resolution was at 10 bits, and the sample rate was at 200 kilosamples per second. From these specifications, we decided to choose a SAR ADC, and SAR stands for Successive Approximation Register Analog Digital Converter. In this thing, we have these basic components, which is an SHA, which is a sample hold, a comparator, a DAC, a digital analog converter, and a control logic, which is the main hard key component of this whole design and architecture. To describe this, the functionality of this architecture, and the analog input is fed into the SNH block, which you saw before in the previous slide, and is being tracked and held. Once it does, then our main logic and algorithm is performed by a binary search algorithm. And this algorithm is implemented by when the n-bit register is first set to a mid-scale value where the MSB is 1. This forces the DAC output voltage to be Vref divided by 2, where the Vref is the reference voltage provided by the A to D. A comparison is done when to see if the input voltage is less than or greater than the DAC output voltage. If input voltage is greater than the DAC output voltage, then the comparator output is logic high, or 1. Then the most significant bit of the n-bit register is still at 1. In the other case, if the input voltage is less than the DAC, then the comparator output is low or a 0. And then the MSB, or the most significant bit of the register, is set to 0. Then the SAR control logic, which we have and built, then moves to the next bit down and forces the high bit and perform another comparison. This sequence continues down to until the least significant bit. Once this register is done, the conversion is complete. Then the n-bit digital word, or the value that we are looking for, is available for the register and is being outputted as the A to D converter output, as you see in the structure. And as you see here, there's an example of how we put an input voltage and it's doing this binary search algorithm. And some of the things that key components that we built off of was an inverter, a NAND gate, and a NOR gate. An inverter is a simple structure, as you see in this orientation and this structure fed, that the gates are tied together in input and the drains are tied together and to make an output. And for the NAND gate, we use 2 PFETs and 2 NFETs in this orientation. And for NOR gate, it's the same orientation as the NAND gate, but the PFETs and the NFETs switch places. Another basic components that we use are the T gate and the 3-gate switch. The T gate is basically a PFET and an NFET that are facing each other with their bulbs tied to the 3.3 volts and the ground. And their gates are tied to P voltage bias, P voltage bias, and N voltage bias. And their sources and drains are tied together, either inputs and outputs. And our gate switch, our 3-gate switch, is created by 1 inverter and 2-gate switch.
Now let's break the system down to 4 components: a sample and hold, a comparator, a digital to analog converter, and an SAR. A sample and hold circuit is used to sample changing analog signal at specific frequencies and hold the signal level constant for the rest of the clock cycle. It can be simply implemented with an NFET switch and a load capacitor. When the clock signal is high, the switch is closed and signal is sampled. When the clock signal is low, the switch is open and the output voltage is held constant. The clock's duty cycle is chosen to be 1% to ensure signal is held for most of the time. To test the sample and hold circuitry, a sine wave is fed to the input and the clock frequency is set to be a few times faster. From the transient analysis plot, it is clear that the signal is indeed sampled at each duty cycle and held constant for the rest of the time. Therefore, the component is successfully implemented. An open-loop comparator is selected for its simplicity and flexibility. It is essentially a two-stage op-amp without compensation, because precise gain is not required for this function. The load capacitance can be chosen to control the charge time. The smaller the capacitance, the shorter the charge time, and the smaller the propagation delay will be. The comparator is tested by feeding in a DC voltage as negative input and a piecewise stair voltage as the positive input. From the plot, when the red DC voltage is larger, the comparator output is low at ground. When the DC voltage is smaller, the comparator output is high at VCC. For the digital to analog converter, a binary weighted capacitor array is chosen. Each capacitor is switched between reference voltage and ground depending on the input code value. To further modify the design, a two-stage approach is implemented. The array is divided into two parts plus a coupling capacitor. This method will decrease the total capacitance and therefore decrease the power consumption and area. The DAC is built with switches which are previously built at transistor level and made into hierarchy blocks. To test the DAC, 4 bits of data are clocked at binary scaled frequencies, with LSB having the fastest clock. An ideal DAC should output a staircase waveform going down with constant spacing. The result is nearly perfect with few spikes at clock edges.
In order to build the SAR, we need to get the flip-flop first. So this is the schematic of the T-gate based flip-flop. We use the NOR gate instead of NOT gate to let the set and reset work. If the clock is idle, the current data will stay at the master loop. When the clock is active, the data will load from the master loop to slave loop, and the new data will come into the master loop. For testing the flip-flop, we can see that when the input changes, the output does not change until the next rising edge of the clock. Now let's look at the SAR with logic. This input of the SAR is from the comparator. The first output of the SAR is 1000. After it goes through the DAC and comparator, it will give us either 1 when input is greater than the DAC output, or 0 when the input is smaller. Let's see, if the data from the comparator is 1, it will set the MSB to 1. If it is 0, it will set the current bit to 0. In both cases, it will shift the test bit 1 to the right for 1 bit, and keep comparing the new data with the input until it loads all the data in the register. For the testing, we build the 4-bit SAR since the simulation for the 10 bits is too slow to get it. In order to get the 4 bits output, we actually need 5 cycles to do that. The first cycle is to reset and clear the register. Then it will read the data. For the testing, I put the data 1011 one by one to the SAR and check the output of the SAR. We know that the data will be complete at the 5th cycle, so we move the cursor to the 5th cycle and read the data. It is the 1011 for all the bits at one time, which is good. For another 1001 as the input, the SAR gives us the 1001 at the 5th cycle.
This is the final schematic of the 4-bit ADC that we have. Unfortunately, we were not able to implement the 10-bit ADC because the sheer complexity of the circuit caused the program that we were using, Multisim, to crash. So we wanted to settle at a 4-bit implementation and basically say why it would also work at a 10-bit implementation. So as we see here, we have the sample clock and the sample and hold circuit, the comparator, the 4-bit shift register, and the 4-bit DAC. What is to note of importance here is the SAR clock, which has been set to 2.2 megahertz. Now, this is the clock speed required by the 10-bit ADC to work correctly. We wanted to ensure that our 4-bit implementation also worked at this high speed, and that's why we have chosen this SAR clock value. In order to account for the difference in bits, we had to change the sample and clock and the reset clock to 1/5 the SAR clock speed. This is because we wanted the the 4 bits of the voltage value to be evaluated at the first 4 clock cycles, and and the value to be held again for one additional clock cycle before being reset. If we wanted to do the same thing with a 10-bit ADC, we would have to set the reset and the sample clock to 1/10 the SAR clock value, which would allow us which would allow for the sample to be held for 11 clock cycles, where the first 10 bits would be evaluated at the first 10 clock cycles and would be held, and the value would be held for another clock cycle before being reset. Although we built a 4-bit implementation, we have lesser resolution, but this did not prevent us from getting good results. As you can see here, in the first test case, we tested a DC input. The input voltage has been held at 1.85625 volts. And we had the simulation run, and as you can see, the blue line, which is the DAC voltage, is originally set to 1.65, and the reset is active. Once the reset goes down, the data has been sampled before, and at that voltage, it's set to 1.65. The DAC then understands that the input voltage is higher than the DAC voltage, and as a result compensates by by setting the second bit of the DAC to 1 volt, which causes the DAC voltage to change to 2.4607. And as you can see, the logic explained earlier follows, and you can see that it originally holds the value at 1.8502. This causes a voltage difference of 6 millivolts, which is far, far less than the 1 LSB voltage value. We also wanted to test for the dynamic range of the ADC, so as a result we went for the upper limit and the lower limit. For the upper limit, we can see that the DAC voltage is very, very closely approximated to the input voltage. Again, we have a difference of less than 1 LSB, about 3 millivolts. For the lower limit, also we can see that the DAC's the shift register and the SAR logic is working perfectly, and we're getting almost no difference in the lower limit. We also wanted to have fun with our project, and as a result we tried to actually see if it worked for a pure analog signal. So we chose a simple analog signal, which is a sine wave, and we tried to see if the circuit that we've built could approximate it correctly. And due to lack of resolution, however, it's not been able to track correctly, but in case if we had 10 bits, we were pretty sure that it would track almost perfectly, because as you can see, the voltage being sampled here is higher than the DAC voltage, and as a result goes up and follows the correct logic and is giving us a reasonable result for the low resolution that we have. Now, talking in terms of power consumption, we're getting into performance standards. The power consumption versus input voltage, this is for the sample and hold. As you can see, as the input voltage on the sample and hold goes higher, the power consumed by the circuit also goes higher. But this is nothing to worry about, because we're looking at a 10 picowatt range, which is pretty small according to these previous circuits we've had to deal with. And this is the power consumed by the sample and hold, which is 9.03 at 3 volts. The DAC consumed around 141 picowatts. The shift register, however, consumed a significant amount of power, which is 1.23 nanowatts in comparison to the other two components, bringing the total power to almost 1.38785 nanowatts for the entire 4-bit ADC. It's a quite low power compared to the previous power levels we have had to work with. But what was interesting is that the comparator did not seem to consume any power, no matter what the voltage was, which is surprising. Another factor that we had to look into was the area calculation. There were two kinds of transistors used in our main design. One was the 45 nanometer and the 90 nanometer, 45 nanometer, 90 nanometer transistor, which has a W/L ratio of 2. This was chosen to ensure that it had the least low power consumption and the least area. But unfortunately, for the transistor gates that we used in our D flip-flops, this small size caused the D latch to fail and had some latching problems. Therefore, we had to reset the W/L width to 100 micrometers. So we had two kinds of transistors coming out. We had ones that were sized at 45 nanometers and ones that were sized at 100 micrometers. So we also had to build a couple of logic gates from scratch from using transistors. As a result, we had to use both kinds of transistors for the NOT, NAND, NOR, and OR, and the T gate separately. And as you can see, these are the area values that we have calculated. Moving to a higher level of hierarchy, we also had the D flip-flop, which used 4 transmission gates and 4 NOR gates. And it occupied quite a bit of area, more than we were expecting. At the highest level of the hierarchy, we had the shift register, the DAC, the comparator, and the sample and hold circuit. And as you can see, we've tried to quantify these components on a bit level basis, whereby if you needed to build a 1-bit SAR, you would have to use 2 + 1, 3 flip-flops, 1 OR gate and 1 NOT gate. So this will allow people to easily copy our schematic and open it to an n-bit system. And as you would expect, the area would scale by these formulas, and the total area that we calculated for a 4-bit system turned out to be almost 0.88 millimeters squared, which is quite big, but I'm assuming it is justified because we have chosen real small values because we wanted to consume lesser power.